Hey, what's up, guys? Welcome to my algebraic geometry lecture. So now I will make some small videos and collect some basic fact so that we can proceed. Because I find that algebraic geometry has some many non-trivial exercise. Probably not non-trivial, but some exercise which is not so easy and but it's important, right? So if you don't do any exercise, then you cannot learn it. Then you will stop. So maybe at some point that I will post some videos that provided the necessary conditions or at least some exercise which is not so difficult, but which we can pursue. Okay, so this is very simple. The localization at prime ideal is a local ring. This is the common fact that we will use in algebraic geometry. So basically, the starting point is that you have some commutative ring with identity, and you take some prime ideals, and you can define AP to be the A minus P. So it's A the ring minus that prime ideal. So this is prime ideal. Then you do the localization of A, and the important factor which is important in algebraic geometry is that this AP is a local ring. Okay, so which local ring means that there exists a unique maximum ideal. So maximum ideals already exist for any ring by using the Zone's lemma, but the non-trivial part is unique. Okay, so recall that AP by definition can be written as A divided by B, where A belongs to A and B do not belongs to P, because this is the definition of localization. Okay, so the proof is that we need to find a unique maximum ideal. Okay, so the answer will be PAP. Okay, so it's not so trivial, but maybe you need to think a little bit. So PAP is A divided by B, where A times P, right? So will be P, and the B will be now belongs to P. Okay, so you can easily check that these guys are ideal. Okay, so the thing that we want to prove is that we want to prove PAP is maximum ideal. Okay, the problem is that how do you prove something is a maximum ideal? I mean you can do the quotient, right? You can check the quotient. Okay, but basically another fact that we can directly prove is a unique maximum ideal is that we start from PAP and this is AP, and let's say we collect some ideal, let's call I, which I do not see PAP, do not see inside PAP, and if we can claim that I is the same as whole ring, then we prove that PAP must be a maximum ideal. This is by definition. Okay, so if I can say that if for any ideal which is not the same as PAP, and if I claim that I is a whole ring, then by definition, right, there's no ideal between PAP and AP, then PAP is also a maximum, and by definition is also unique. Okay, because if you have another maximum ideal which is different from PAP, then this guy must be AP. Okay, so this is our goal. Our goal is to show this. Okay, so our goal is to let's say we take I do not the same as PAP. So basically this tell you that there exists the AB where element in the ring such that I is different from PAP. So remember that the PAP is the A divided by B, A belongs to P, P do not belongs to P. So the only possibility is that there is AB belongs to A such that A belongs to A divided by B belongs to I, and A do not belongs to P, and the B do not belongs to P, right? Because if A belongs to P, then by definition that then you will see inside PAP. Okay, but so we have this. But if this is true, then what? Then obviously that B divides to A will also in AP. The reason is that B divides because A do not the same as do not inside P, right? So in a denominator, B divides A by definition is still in AP. But let's tell you that A divided by B and the B divided by A will be 1. Okay, so 1 will inside I. Okay, so if an ideal which connects the unit will tell you that I must be what? I must be the whole I must be the whole ring. Okay, so I will be AP. Okay, so if I must be AP, then by definition that PAP will be a unique maximum ideal. So usually AP divide quotient PAP usually denoted by kappa of P. This is called the residual field, and we will talk about the fact or the consequence between this localization of prime ideals, which is important in the spectrum in the fine schemes. Okay, see you next videos.